Good afternoon, Dr. Burton. My name is Elizabeth Hughes, and I'm excited to be spending a little time with you for my article reflection, where I'll be connecting geometric thinking to coaching and classroom practice. So let's begin with why geometry matters. Geometry is one of the most critical, yet most overlooked areas of elementary mathematics. As Crumpton and Ferguson explain, although geometry is important, it is often ignored by curriculum writers and teachers into high school, which results in missed learning windows where children begin to form shape concepts in early preschool years, which can stabilize as early as age 6. That statement resonates deeply with what I see in Alabama classrooms every single year. In our state, geometry and measurement are consistently the lowest performing and most heavily weighted domains on the ACAP assessment. That combination tells a story, not of student inability, but of missed opportunity. When geometry is pushed to the end of the pacing guide or taught as a standalone spring unit, students rarely experience the rich and continuous development of geometric reasoning that they need in order to succeed. And as you can see here, our ACAP mathematics domain performance, when you take a look at geometry and measurement, it ranks at 47%, which is our lowest testing statewide average. So, as a K-5 math specialist and a coach mentor, this realization shapes a lot of the work that I think is important to do with teachers and coaches. Together, we explore how to move geometry experiences earlier in the year and connect them across units, and intentionally weave spatial reasoning into daily instruction. So, some of the key concepts from the research articles that I read: Berger and Shaughnessy, as well as Crumpton and Ferguson, they ground their work in the Van Hill model of geometric thinking, which is a developmental framework that describes how students move from simple recognition of shapes to abstract logical reasoning. As you can see here at level 1, which is visualization, children identify shapes by how they look. They might say things like, "That's a rectangle because it looks like a door." At level 2, analysis, they begin to identify and describe attributes like sides and angles. By level 3, abstraction, students start to reason about the relationships. Why are all squares rectangles, but not all rectangles squares? Berger and Shaughnessy remind us that these levels are not strictly tied to age, but rather to instructional experiences. They emphasize that students cannot simply skip levels. And it's a reminder that resonates in professional learnings that I do with teachers who often wonder why upper elementary students are still describing shapes by their appearances rather than their attributes. So, in our reading, Crumpton and Ferguson, they expand on the Van Hill framework by naming these four essential understandings for elementary geometry. Number one, recognizing and comparing shapes by attributes. Developing, number two, developing spatial orientation and perspective. Number three, composing and decomposing figures. Number four, understanding motions, transformations, and symmetry. They argue that these understandings are the foundation for spatial reasoning and, surprisingly, problem solving, which are two skills at the heart of higher order mathematical thinking. So, what are my implications for K through 5 in practice as I am connecting research to the coaching work that I do? The connection between research and practice is ultimately where my work as a specialist comes alive. When I observe lessons or co-plan with teachers and coaches, I'm always listening for the type of reasoning students are using. Is it visual? Is it analytical? Is it abstract? And being intentional about designing those next steps that help move students along that continuum. So, for example, in first grade, I've modeled lessons where students compose and decompose shapes using pattern blocks to make animals or houses, prompting them to name and describe what smaller shapes they see inside. These experiences build level two analytical reasoning without ever having to say the words Van Hill. In third grade, we consistently classify quadrilaterals by attributes instead of naming them by memory, which directly supports Crumpton and Ferguson's emphasis on recognizing that shapes can look different within the same category. In fifth grade, we introduced coordinate planes earlier in the year. We like to use map-based projects where students graph playground layouts or classroom furniture or bedrooms. These tasks intentionally strengthen the spatial orientation and perspective strand that Crumpton and Ferguson found missing from many of our curriculum sequences. So as you can see here, here is a great example of an activity that can be used in kindergarten or first grade to help students recognize and compare shapes by their attributes. Having them find and circle some of the shapes that they recognize in the picture and use just some common language to describe how they recognize those shapes. Here's another great example of an activity for first grade that could have students compose and decompose figures. I think that this also allows them to develop spatial orientation and perspective as they are orienting the shapes in different ways in order to compose or decompose the larger shapes that they are building. So, why does all this matter for Alabama? As we're bridging theory to our state data, what stands out most is in my current work is how this research connects to statewide testing and curriculum design. When I pull ACAP data for schools I support, the same trend appears time after time. Geometry and measurement are the lowest performing areas across grade levels. Yet, these are the most heavily weighted in mathematics domains. This mirrors the national pattern that Crumpton and Ferguson described when they wrote that a large majority of children in the United States have insufficient understanding of geometric concepts and lack skills in geometric reasoning and problem solving abilities. The authors warned that instructional delay could result in crucial windows of opportunities being missed. That statement is a call of action for instructional leaders like myself. When geometry is postponed, we deny students access to experiences that could strengthen not only their spatial reasoning, but also their conceptual understanding of number, measurement, and algebra. That's why in my coaching sessions and in my curriculum mapping meetings, I encourage teachers and coaches to embed geometric thinking throughout the year in number talks, in measurement tasks, and even in data lessons. Geometry should not be an isolated unit. It's a continuous thread of mathematical reasoning. So, as I'm looking at our instructional strategies that align with research, Crumpton and Ferguson constructive approach and the Van Hill instructional phases encourage us to focus on these ideas. Hands-on exploration. Use the manipulatives like geoboards, tangrams, and whitebook sketches to construct meaning. Mathematical talk. Encouraging students to describe attributes and justify their reasoning as they're listening to peers. This in itself helps move students from a level one to a level two thinking. Integration across content, embedding geometry and science and art and technology. For example, exploring symmetry through robotics or even garden design. And number four, continuous assessment, noticing whether student reasoning aligns with their developmental stage, as Crowley emphasized, teaching at the right time for cognitive readiness. When coaches and teachers design learning experiences this way, we can see a shift from memorization to reasoning. The very shift that both Berger and Shaughnessy and Crumpton and Ferguson describe as the heart of geometric understanding. So, in reflection, here's a call of action for myself as I consider my coaching next steps. These readings reinforce what I've observed across classrooms in our region. Geometry and spatial reasoning are not side topics, they are essential foundations. Every time a teacher says, "Oh, we'll get to geometry after testing," I think about Crompton and Ferguson's reminder that geometry and spatial reasoning form the foundations of learning in mathematics. My goal as a coach mentor is to help teachers and districts reposition geometry as a year-long habit of thinking, not simply a springtime checklist. When students see, describe, and manipulate the world through geometric relationships, they develop reasoning skills and elevate every other math domain. So, in short, when we give geometry the time and attention it deserves, starting in kindergarten and embedding it throughout the year, we're not just improving test scores, we're cultivating mathematical thinkers who can visualize, reason, and problem solve far beyond the classroom. So, here's our reflection and call to action. Geometry and spatial reasoning form the foundations of learning in mathematics. So it's important that we make that shift from geometry as content to geometry as thinking. Here are the resources used for this reflection, and I thank you for listening and spending some time this afternoon hearing my thoughts. Thank you. Have a great afternoon.